Hello and welcome to our video on the design of agitation systems. In this video lecture, we get to know what agitation is, how do we design standard agitation systems, how do we estimate its power requirements, and how do we scale up or scale down from existing agitation systems. Let's begin. First, what is agitation? Agitation is just a technical term for mixing. No, when we say that we are agitating something, it just means that we are trying to mix fluids. Agitation is a general term that we use to refer to the mechanical mixing of either one of the following scenarios. It's either you're trying to mix two miscible liquids in a tank, you're trying to dissolve a solute in a solvent. Say, for example, you're trying to dissolve sugar in water. You have to mix it, right? Or you might want to be dispersing gas bubbles in a liquid. This oftentimes happens with things like spargers. Or you want to prevent the settling of solids in a slurry. This happens with insoluble solids that you're just trying to disperse throughout the fluid. It might be because it's a catalyst, or it might be because you're just trying to produce a consistent slurry with well distributed solid particles. Or you can even do mixing simply just to increase the heat and mass transfer coefficients. As you know, introducing turbulence into something will inevitably increase the rate of convective heat and mass transfer. So a lot of stuff are very dependent on the design of mixing systems. If you're still unsure of what an agitator looks like, you can simply think of your blender as something that is a very small agitator. But of course, what we're talking about here are large-scale mixers or large-scale agitators. This is what the schematic of a standard agitator would look like in a large scale. You would have, of course, your tank itself. It can be a very simple cylindrical tank, or sometimes it's not even cylindrical. You can have cubic tanks. But in general, you have the tank to hold the fluid inside. Okay, that's the mixing tank. The second main component of an agitator is the impeller. The impeller is right here. You can think of it as the blade that is responsible for mixing or churning the liquid. It promotes mixing by transferring mechanical energy to the fluid. In specifically, what you are transferring is shaft work. So there's a motor here. Sorry, there's going to be a motor here, no? And this motor is transferring shaft work or mechanical energy into this impeller. We call this long one the impeller shaft. The impeller itself is the blade in here, no? And the design of the blade is very much influential as to how much energy will be consumed by mixing this liquid. And the third major component of an agitator is a baffle. A baffle or baffles are provided such that we are able to prevent the formation of vortices to maximize mixing. What we're talking about here is we don't want to form a single vortex at the middle. So if we take a look at the top view of this agitator right here, we would expect, say for example, it's a cylindrical tank. So at the middle here, you have the shaft, no, of the impeller. And if you don't provide baffles, baffles are usually placed at the side of the mixing tank. If you don't provide any baffle, what you would end up forming is a one singular vortex, a one big vortex at the middle. Now, as you start mixing that in a rotational matter, and this vortex mixing, no, actually promotes laminar flow that is in the rotational direction. And as we all know, laminar flow is not good for mixing because under laminar flow, the layers of the fluids do not mix with each other. They just stay as individual layers. So what we want here is not the formation of a single vortex, but the formation of many vortices, many smaller vortices, which are akin to turbulent flow, because in turbulent flow we have what's called eddies, right? Eddies are technically just small vortices, and the more of this that you have, then the better mixing you would have. So the effect of the baffle would look like this. So say for example, we have the same agitator, but instead of it just being bare in the sides, we have several baffles installed Commonly we have four baffles. You might be able to see this with your washing machine, with your blender, no, anything that promotes rotational motion. Oftentimes you would see baffles, usually four baffles. And if you start mixing this, you will not be able to produce one singular big vortex at the middle. Instead, what you end up doing is you're promoting the formation of smaller vortices. And if you have four baffles, most likely you would see four smaller vortices, each at the quadrants, no, of the mixer or of the agitator. And by doing this, no, by doing this simple addition of a baffle, we are able to produce turbulent flow in the rotational direction that really helps in mixing. So those are the three main components of an agitator. Of course, there are many other components, and we will discuss these measurements later for the design of a standard agitator. As I mentioned before, this is what happens, no, if you place baffles. So these are your baffles. And if we place the four baffles inside of a cylindrical tank, what you would see are four smaller vortices. This is your impeller blade at the very center. Baffles prevent the formation of a central vortex that limits mixing by diffusion through liquid layers only. In short, without baffles and with slow mixing speed, oftentimes you would just have diffusion as your limiting mass transfer mode. But if you install baffles and by increasing the rotational speed of the impeller, what you're promoting is convective mass transfer. And we all know that convective mass transfer is faster compared to simple diffusion mass transfer. And that is achieved through turbulent mixing. Now, in this slide, we see the design of a standard agitator. Now, we call this a standard agitator because it's based on decades and decades of experience that this proportions for a standard agitator are working very good for even different sizes or different scales. No, so the standard tank diameter to water level ratio is 1, meaning the height of the liquid inside of the tank should be roughly the same as the diameter of that tank. No, uh, notice that we are describing this as the water as the liquid level ratio, not necessarily just water. Liquid level ratio because it's possible that the actual diameter of the tank, no, is larger than the height of the fluid inside, and that is reasonable, right? For many design reasons, because you would not design an agitation system wherein the intended liquid level height is the same as the height of the tank, right? Because there's a very big risk of spillover once you start spinning this impeller. No? So usually we give an allowance, so some sort of allowance between the intended tank height and the actual tank height, so as to prevent spillage. But in for design purposes, we usually say that the allowable, no, or the optimal liquid level height would be the same as the tank diameter. Now, the next ratio is also important. It's the blade width to impeller diameter ratio. That's W over DI. D sub I is the impeller diameter. It's this one. No, it's the diameter of the blade itself. While the blade width, as you can see here, is the thickness of this blade. Usually we set it into 1/5. Some designs have set this into 1/8. You would see later what's the difference between 1/5 and 1/8 once we start discussing how much power this consumes. Because this ratio right here very much has an effect on the power requirement of this impeller to steer. Another parameter is baffle width to tank diameter ratio. The baffle width we signify by the parameter J. That's the thickness of the baffle that we install. It's usually 1/12. Now you can somehow veer off, no, this established ratio, but the problem with providing a what do you call this, a thicker baffle is that there is a chance that the impeller, no, will collide with the baffles, and we don't want that happening because that will damage both the impeller and the motor. We usually keep it just small, just so enough that we are able to to break that one singular vortex and instead promote the formation of smaller vortices. But we don't make it big enough, no, so that it might cause accidents. Also, this is also considering expenses due to material costs. No? And the final ratio that we should always look at is the blade length to impeller diameter ratio. The blade length is the other parameter that is related to width. So width is, if we are looking at it right now, this is the side view of the agitator. The blade width is technically the height of the blade, and the blade length is really describes how long is the blade in relation to the impeller diameter. Now, it's also not a good practice to have the length of the blade the same as the radius of the impeller, because these impellers are very carefully designed so that not only they will be promoting very good flow around them, they would also promote very good flow within them. And we need to leave a gap, no, right here at the space here between the blade itself and between the central shaft of the impeller for many different reasons. This has mass transfer implications. This has hydrodynamic implications. So, by decades and decades of experience and experimentation, we just see that this is a very good blade length to impeller diameter ratio. All of this are just based on experience. No, these are things that people just decided because it just works. No, it gives us very good performance in terms of power consumption versus volume mixed. It gives us other benefits. Say for example, it's easier to clean setups like this. They are easier to build, and so on and so forth. The one thing that you need to keep in mind that this is not a very strict system. Now, of course, you can vary more beyond this standard sets of ratio, but of course there will be trade-offs. For our purposes, we're going to follow this standard ratios. Now, the main thing that we have to learn about agitators, of course, is the power requirement. We are very much interested in how much power this will consume because, as you all know, mixing stuff requires power. No, it requires energy. Remember that you are providing a motor, and the motor consumes electrical power, and that electrical power is transformed to mechanical power to drive that shaft. So of course, uh, it's important for us to know how much power that will consume. And we're going to introduce a parameter called the power number. The power number is written here. The power number is a dimensionless number, and it consists of the following terms. You have here power, Gc, over density of the fluid inside. N is the impeller speed, and d sub I is the impeller diameter. The power number, as you can see, relates the parameter of power, and you can see how power is related to the other parameters. So if I rearrange this equation, I can write this as power. I'm going to add GC just for a what they call this, unit conversion. But remember that that GC here is dimensionless. So power is equal to the power number multiplied by density of the fluid times impeller speed cube times impeller diameter raised to the fifth. Now you can see here clearly what parameters influence power consumed and how much do they influence it. First and foremost, density. The power is directly proportional to the density of the fluid. What does this tell us? It tells us that more dense liquids would require more power for mixing, which makes sense, right? If you're trying to mix a tub of mercury, mercury has a density of 13,600 kilograms per cubic meter. That would be very hard. It requires more power just because of its sheer density. No? So density has a linear effect on power. Next parameter is impeller speed. Power is shown here to be directly proportional to the impeller speed raised to the third power. So the faster that you want the impeller speed to spin or to turn, of course, the more power you would consume. Same thing with your with your other impeller based appliances, say for example an electric fan. For an electric fan, you have different speed settings, and if you turn up the speed to the highest setting, just know that you are consuming the most power for that electric fan. Okay, so for agitators, power is directly proportional to the cube of impeller speed. So impeller speed has a big impact, no, on the power consumed. The last parameter here is impeller diameter, and it has an even greater effect on the power consumed. The power is directly proportional to impeller diameter raised to the fifth power. Just imagine how hard it is to spin, no, an impeller with a very big diameter. It takes a lot of energy to get that moving and to keep that moving. That's why impeller diameter here has such a large influence on the power consumed. That's also the reason why we don't necessarily want to always maximize that the impeller diameter would be very big such that it fits the diameter of the tank, no? Because it has a very big implication on the power requirements. Also, another very good thing to note here is that impeller speed and impeller diameter are inversely proportional for the same power level. If you look at the relationship at constant power, the relationship is that the cube of impeller speed is inversely proportional to the fifth of impeller diameter. The implication of this one is that if you want to maintain constant power, but if you want to increase your impeller diameter, what would happen is that you would operate that at a lower impeller speed, which makes sense, right? For a given amount of power, but if your impeller diameter is larger, then that would have to spin slowly or slower if you want to maintain just the set amount of power that you were doing before. So this power number expression gives us a lot of insight as to how working parameters inside of an agitator influences how much power it consumes. Okay. In the handbook, we also have this power number equation. So let me just open the handbook. This is in chapter 6 in fluid mechanics. So in the fluid mechanics or fluid and particle dynamics section of this one, you have a section on agitation or mixing. It's this one, fluid mixing. On the ninth edition, that's page 6-33. In here, you can see the power number. Okay, it's this one. This is the power number. It's equation 6-165. Just take note that this is missing GC. No, GC is a very important relational parameter here, such that the power that you get here would be in the standard SI unit, like watts or kilowatts. But the GC here is provided, say for example, if you want to use English units, so that we would have a correct conversion between mass and force. Okay, so just take note of this additional variable here, GC. Now, another parameter that is important for the design of agitators has something to do with the impeller speed, and that is, of course, the Reynolds number. The Reynolds number, as we have already previously discussed, is important for us for judging if a flow is laminar or turbulent, right? And the usual appearance of the Reynolds number is designed for fluid flow inside of pipes. That would be du rho over mu, meaning diameter times fluid velocity times density over viscosity. That's because this is designed for fluids flowing inside of pipes. But for different flow configurations, like for this agitator, we simply swap the impeller the fluid velocity. We swap that out with impeller speed, and then the pipe diameter, we swap that out with impeller diameter, because the impeller diameter gives us so much information about the design of agitation systems. For the Reynolds number, we have this expression: impeller diameter squared times the impeller speed times density over viscosity. Now, a few notes for this one. You all know that the Reynolds number is a dimensionless number, and for that to happen, if you're using standard SI units, the impeller speed has to be given in revolutions per second, or simply hertz, or simply per second. Okay, that that's because your parameter like viscosity, if this is in standard SI unit, will be in Pascal second. So you have to cancel this this unit of seconds here. You cannot use revolutions per minutes or RPM in this impeller speed here. Okay, so that's just a quick note. In the handbook, the Reynolds number is also given here. It's equation 6-164. This is Reynolds number for a steered tank agitation. Okay? Okay. Now, how do we relate the power number and the Reynolds number in order to determine the power consumption in steering or in agitation? We have this graph. This graph, as you can see, the y-axis is the power number, the x-axis is the Reynolds number, and then we have 5 different curves. Each of these curves correspond to a different blade design and a different baffle width to diameter ratio, which I will discuss later. But this is a very simplified approach for us to be able to know that for a given Reynolds number and for a given impeller design and ratio, we can easily relate those two parameters and get the power number. And once you know the power number, it's easy for us to now calculate the power required for agitation, right? This is from another textbook, but in the handbook, we have a clearer version of that. And it's this graph right here. As you can see, it's the same. The y-axis is the power number, x-axis is the Reynolds number, and then you have here the 5 different curves. This individual curves correspond to different blade designs. So you can see here the top view of the different blade designs. Some of them have central discs. For example, curve 1, as you can see, has a central disc. Same with curve number 3, and then from there you have your blades attached. Curve number 2 doesn't have a central disc. Same with curve number 4, but both of them have straight blades. Curve number 5 has a curved blade, and curve number 6 have oblique blades. No, they are angled slightly. And notice that in the laminar flow region, no, the design of the blades have very minimal influence on the power consumed. But in the turbulent flow region, you can see that the power number becomes constant for highly turbulent regions, and it differs from blade to blade designs. You know, this is actually a very good point for if you're trying to keep your mixing at higher Reynolds number. It means that your power number would be constant, and it means that your power is just simply proportional to density, impeller speed, and impeller diameter. No. So we can use this graph to estimate parameters for our agitator. Let's have an example and solve this problem. And let's illustrate now how to use that figure. Let me get this problem. Okay, the problem reads, it is desired to agitate a liquid having a viscosity of 1.5 times 10 to the minus 3 Pascal seconds. Let's just write that down. And a density of 969 kilograms per cubic meter in a tank having a diameter of 0.91 meters. The diameter of the tank, 0.91 meters. The agitator will be a 6-blade open turbine having a diameter of 0.305 meter operating at 180 RPM. So some important stuff here. It's a 6-blade open turbine, which as you can see here, these are designs for six-bladed turbines. So And the impeller diameter is given here as the 0.305 meters. And it's operating at 180 RPM, meaning the impeller speed is 180 revolutions per minute. I'm writing it this way so that we don't forget to convert to revolutions per second. The tank has 4 vertical baffles, each with a width of 0.076 meters. Baffle width 0.076 meters. Also, W is 0.0381. What is W? W is the baffle width. Sorry, not baffle width, impeller blade width. And impeller blade width, along with the impeller diameter, are the important parameters that we need for this design uh, of uh, of what do you call this? For this different curves. If you notice, it's a little bit blurred here, but you will notice at the bottom here you have the parameter W over D. This is exactly the W that we described as the impeller blade width, and D here is the impeller diameter. So you have options here for curves 1 and 3. They're both the one with the disc, but the first one is 1/5. The curve 3 is 1/8. And then for curve 2 and 4, they are the same design, but the first one is 1/5. The second one is 1/8. So that's the main difference between those two, right? So let's calculate what is our W over D ratio. Blade width over impeller diameter. For a blade width of 0.0381 meters and impeller diameter of 0.305 meters, this is the result, 0.125. This is roughly 1/8, right? So in terms of ratio, yeah, 1/8 is 0.125. So it means that we have an open turbine. An open turbine is the one without the disc. And then this is an impeller blade to impeller diameter ratio of 1/8. Therefore, we're just going to use curve 4 in our design. So that's how you decide, no, between whether to use curve 1 or curve 3 or curve 2 or curve 4. In some instances, we can even just straight up say what the type of turbine is and just use that curve. Excuse me. So now that we know that we're going to use curve 4, we first have to look at where curve 4 is. It's a little bit unclear in my copy here, but just refer to your physical handbook and you will see this more clearly. Curve 4 is right here. So it's this line right here, this one. This horizontal part, and then it increases here. Okay, let's trace that out with red. Okay, this is curve 4. Okay, that's curve 4. The other branch here clearly is marked as curve 5, so you can easily distinguish between the two. Okay, now the problem is asking us to calculate the required power in kilowatts, and the way on how we do that is very simple. Get the Reynolds number, get the curve number, of course it's curve number 4, get the intersection of this, and then get the power number. From the power number, you can estimate the power requirements. Okay, first, Reynolds number. That's impeller diameter squared, impeller speed, density over viscosity. Just be very careful with the units. Let me show you. Impeller diameter is already given in meters. We can use that directly. 0.305 meters squared. Impeller speed is in revolutions per minute. Let's quickly convert that. From revolutions per minute to revolutions per second, that's 80 divided by 60. 180, sorry. Let me restart my calculator. That's 180 over 60, that's 3 revolutions per second, or simply just a unit of per second or hertz. The fluid density was already given as 969 kilograms per cubic meter. If you're not given this, then look for its density in the handbook. And finally, viscosity is also given as 1.5 times 10 to the minus 3 Pascal seconds. If you take a look at the cancellation of units, you would see that what will cancel? Okay, let's take a look at the units. You have here square meter, and then per second, and then kilogram per cubic meter, and then at the bottom you have Pascal second. We know that Pascal is Newton per square meter, right? So this would simplify as Newton. In the denominator, you have Newton second squared cubic meter. In the numerator, you have meter to the fourth and kilogram. So right now, we can simplify this as cubic meter will cancel out. What remain is meter kilogram per Newton second squared. Now, what is Newton? Newton is kilogram meter per second squared times second squared meter kilogram. As you can see now, second squared cancels out, meter cancels, kilogram also cancels. This is a truly dimensionless number. That's why you have to be very careful with using impeller speed. It has to be revolutions per second, otherwise it will not, the units will not cancel out. Let's get that out of the way. Now we can calculate our Reynolds number. That's impeller diameter squared times impeller speed times density over viscosity. My Reynolds number is 180,282.45. I'm just going to write that as 180,282. Because if you take a look at your graph, you don't have to be very exact about it because this is a logarithmic chart both in the x-axis and in the y-axis. So we need to just convert that into an exponential form. This is 10 raised to 3. This is 10 raised to 4. So my Reynolds number is 1, 2, 3, 4, 5, 1.8 times 10 raised to 5. And it's your task now is to locate where is this 1.8 times 10 raised to 5 Reynolds number here. This is 10 raised to 4. This is 10 raised to 5. So obviously, our actual value is beyond this 10 raised to 5. No? But luckily for us, it just means that this curve right here for curve number 4 just continues and continues at a constant power number. So this one right here is already our reference for what the power number is. Okay, so 1.8 times 10 raised to minus 5 is somewhere right here, and you get that intersection with curve number 4. It's right here, and then you can read it on the y-axis on the left. Let's try to make a line for that, and we will now get our power number. This is okay. This is my best estimate for that. Now let's try to read what the power number is. You have to be very careful again because your y-axis here is also logarithmic in scale. This is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3. It's between 2 and 3. I'm going to call it at 2.5. From the graph, our power number is 2.5. And it is from this power number that you're now able to calculate the power requirement. Remember the definition of the power number, that is power times GC over density, impeller speed cube, impeller diameter raised to the fifth. Rearrange this one. The power is equal to 2.5 density impeller diameter, impeller speed cube, impeller diameter to the fifth over GC. Now let's try to substitute everything and look at the units. 2.5 is the power number, it's dimensionless. Density, impeller speed, I'm going to use 3 revolutions per second, cube, and then impeller diameter, meter raised to the fifth power over GC. GC is 1 kilogram meter per second squared per Newton. So right now, this is not important because this will just cancel out. But for the remainder of the terms, take a look at what will happen to your units. So you have kilogram per cubic meter and then per second cube. Remember, this is raised to 3. And then times meter to the fifth. If you simplify this, this will become kilogram square meter per second cube. And if we simplify this, this has to become watts. So 1 watt is 1 joule per second. Joule is Newton meter. Newton is kilogram meter per second squared. Meter per second. And as you can see, this simplifies to kilogram square meter per second cube. So this collection of units right here is equivalent to watts or joules per second. When we try to calculate the power, that will be 2.5 times 969 times 3 cube times 0.305 raised to the fifth power. I'm getting 173 watts. Or in kilowatts, it's 0.173. Double check. 2.5 times density times impeller speed cube times impeller diameter to the fifth. This is our final answer. And that's the very simple way, on how we can estimate agitator power. Just follow these steps right here. Get the Reynolds number, identify the proper curve, because remember that the proper curve is very important in getting the correct power number. No? If we misidentified what the curve is, clearly you would get a different power number. And if you get a different power number, then you would get a different power calculation as well. Okay, that's how we estimate the required power of agitation systems. Now, finally, let's learn how to scale up or scale down agitation systems. When we try to scale up and scale down, what's really important for us to remember is that we're doing so in the sense that we're assuming that our design is standard in nature. And as you remember earlier, we described what a standard agitator looks like, and a standard agitator follows closely, not necessarily exactly the same, but it follows closely this provided guidance ratios for tank diameter, blade width, and all of those other parameters. So when we're doing scale up and scale down, it's just that we're just trying to keep those ratios the same, but we're just making we're just making the entire system bigger or smaller. And with that in mind, everything that has something to do with scaling up or scaling down of agitators is described by this scale ratio R in here. The scale ratio or the scale parameter capital R is the ratio of V2 over V1, or the new volume over the original volume raised to 1/3. And that boils down to simply just having the new tank diameter over the original tank diameter. The reason for this simplification is that, remember that the volume of a cylindrical tank, assuming that of course our agitator is a cylindrical tank, the volume of that would be the base area or cross-sectional area pi over 4 tank diameter squared multiplied by the height of the fluid, which is h. But remember that for a standard agitator system, the tank diameter should be the same as the height of the fluid inside, right? That is our very first point here. Tank diameter over level height is equal to 1, meaning that we can simplify this volume calculation simply as pi over 4 tank diameter cube, such that when we get the ratio of the new volume to the original volume, this is pi over 4 new tank diameter cube over pi over 4 original tank diameter cube. The pi over 4 will just cancel out. And if we get the third root of this one, we get the very simple, the scale up or the scale ratio R is simply the ratio of the tank diameters. So literally, we're just trying to see what happens if you make the tank bigger, and what happens when you make the tank smaller, and all of the stuff inside of the tank will also scale accordingly, no? If the tank becomes bigger, the baffle would also become bigger. The blade width, the impeller diameter, all of those will get bigger, because this scale ratio R, you just multiply to the existing other parameters. Say, for example, if you want to get the new impeller diameter, that would simply be scale ratio R multiplied by the original impeller diameter. Same thing with blade width. The new blade width would be equal to the scale ratio R times the original blade width. No? So think of it as something that you're just trying to scale up one shape, and then everything inside of it follows. No? If you increase the tank, the size of the stuff inside will also increase. And all of them will do so by the scale ratio R. Let's we will see this later as an example. Now, all of this, this scale ratio R has something to do with the physical measurement, no? Meaning lengths or sizes in general. But another important thing for us to remember is that it's a little bit complicated now to judge what happens to your impeller speed and to the power required by the agitator once we make it bigger or once we make it smaller. And to that point, we can still use that ratio R, but it's not a linear relationship anymore. For the new impeller speed, the following relation may be used. N1 over N2 equals R raised to N. This small n right here, has different values. And those are N is equal to 1 if you want to have equal liquid motion, which technically means that you have equal impeller tangential speed, right? It's just that if your small n is equal to 1, this means that N1 over N2 is equal to R. Or for the new impeller speed, that would be R over the original impeller speed, N1. If you want an equal impeller tangential speed, what would inevitably happen here is that your new impeller speed would have to be larger than the original impeller speed if you want to maintain the same tangential speed. The parameter small n becomes 3/4 if your goal is for equal suspension of solids, and it becomes 2/3 if you want to get equal rates of mass transfer or equal power per unit volume. Power per unit volume, no? This is oftentimes expressed in kilowatts per cubic meter. That's power per unit volume, or watts per cubic meter. If you want to keep this equal, then n becomes 2/3. So this are usually coming from experimental data, no? And from a many number of experiments, this is what we see that works as the value of this small n right here to relate for the impeller speed. Okay, the reason for this one, remember, is because of the complicated relationship between the impeller speed and the impeller diameter. No, this is coming from the power number, as you remember. This one, they're inversely proportional. The cube of impeller diameter is inversely proportional to the fifth of impeller diameter. The cube of impeller speed is inversely proportional to the fifth of the impeller diameter. Okay. Now let's try to apply all of those scale up and scale down principles to this example right here. We will get to apply all of those equations that we described. Okay, a turbine agitator having 6 flat blades and a disc has a diameter of 0.203 meters and is used in a tank having a diameter of 0.61 meters and with the same fluid height. Blade width is 0.0405 meters. 4 baffles are used having a width of 0.051 meters. The turbine operates at 275 RPM in a liquid having a density of 909 kg per cubic meter and a viscosity of 0.02 Pascal seconds. The first question is we calculate the power requirement of the agitator and the power per unit volume. And then for letter B, follow-up question, we want to scale up this system to a vessel having a volume of 100 times the original for the case of equal mass transfer rates or equal power per unit volume. So let's answer letter A first. Letter A is very much similar to what we did for the previous example, right? We just want to get the Reynolds number, we want to get what kind of blade it is, and then the power number, and then finally the power. Let's do that first. Okay, some important information that we're going to use. Of course, we need the blade length, blade width rather. The blade width was given, and that is 0.0405 meters. And we are going to use that in conjunction with the impeller diameter, which is 0.203 meters, in order to get the ratio W over D sub I. Let's check. This is 0.199 or this is 0.2. 0.2 is 1/5. So take a look at the description of the impeller. You have 6 flat blades in a disc, and W over D ratio is 1/5. Take a look at your graph from the handbook. You have two options for 6 blades with a disc. It's either curve 1 or curve 3. W over D ratio of 1/5 that we calculated, that is curve number 1. Curve number 1 is right here. Okay, so we will be using that later. After that, we need to get the Reynolds number. That's di squared n rho over mu. I'm going to substitute directly. Keep in mind that your revolution speed was given again as RPM. So that's 275 revolutions per minute. In order to avoid confusion, let's convert that to revolutions per second. That is 275 divided by 60. I have 4.583 revolutions per second or per second. Now substitute everything from in the equation for the Reynolds number. That would be impeller diameter squared times impeller speed okay, I'm going to substitute it directly. 275 divided by 60 times density of the fluid, that's 909 kilogram per cubic meter, over the viscosity of 0.02 Pascal second. The Reynolds number I'm getting is 8584. Or this is 8.6 times 10 raised to 3. Now go back to our graph. Look for 8.6 times 10 raised to 3. This is 1 times 10 raised to 3. This is 1, 2, 3, 4, 5, 6, 7. Okay, this is 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, no, I'm missing one line. Sorry. This is 1, 2, 3, and then this faint right here is 4, 5, 6, 7, 8, 9, 10. Okay. So this first one right here is 1,000. 1,000, 2,000, 3,000, and so on. So our value is 8.6 times 10 raised to 3. 1, 2, 3, 4, 5, 6, 7, 8, and 9. 8.6 is somewhere right here. Okay. This is my point for my Reynolds number. And then, of course, we want to bring that up and look for its intersection with curve number 1. Remember, our identified was curve number 1. This is my intersection points right here. And I'm going to read that for the power number. Power number is 5. That's it. From the graph, power number is 5. And now that we know that, we can now go back to the definition of the power number. That's power times GC over density n cube di to the fifth. Rearrange this one to get power. This will be power number rho n cube di to the fifth over GC. We can now substitute directly. Power number is 5. Density is given, 909. Impeller speed is also given, 275 over 60 cube times impeller diameter raised to the fifth. Impeller diameter is 0.203 to the fifth over GC, 1. Power is 150.85 watts. Okay, we're done with letter A. So this is the requirement for letter A. Okay, power requirement. Power per unit volume. Power per unit volume is simply whatever the power is divided by the volume. Volume here refers to the total volume of the fluid. And we know that that is pi over 4 tank diameter cube if tank diameter is equal to the fluid height h. And it was explicitly mentioned here that your tank diameter is 0.61 meter and with the same fluid height. Okay, so we're safe there. We can now calculate this, the power per unit volume, as the power, 150.85 watts, divided by pi over 4 times tank diameter cube. Do not make the mistake of using impeller diameter here. Okay, it's tank diameter, not impeller diameter. I'm getting 846.19. The unit of this one is watts per cubic meter. Cubic meter because what I use for the tank diameter is also in meters, 0.61 meters. Okay, we're done with A. So this one right here would be our baseline value. Now, this is our original agitator. And our goal for letter B is we want to scale up this system. Okay. Let's have letter B here. The scale up. So in order to make things simpler for us, I'm going to prepare a simple table wherein we have here the original agitator system, and this one is coming from A right here. So all of this in the first page here pertains to our original agitator, and we want to know what are the parameters for the bigger agitator. Okay, of course we will want to know what is the new tank diameter, what's the impeller diameter, what's the new blade width, what's the new baffle diameter. Those are the given values, right? Impeller diameter, tank diameter, blade width, and baffle width. Also, we want to know its new speed and its new power. Okay, so let me just list down some of the stuff for the original agitation system. Tank diameter is 0.61 meters. Impeller diameter is 0.203. blade width 0.0405. Baffle width was also given. So I'm going to include it in our calculation. Baffle width is 0.051 meters. Impeller speed, let's have this as revolutions per minute. It's originally 275. Power in watts, it is, as we calculated, 150.85 watts. Now, how do we get the numbers for the bigger agitator? As you know, it's just a matter of determining the scale up, or the scale ratio, or the scale parameter R. The scale parameter R, as previously discussed, is simply the ratio of the tank diameters. Yung new tank diameter divided by the original tank diameter. Okay, it says here that we want to scale up the system to a vessel having a volume 100 times the original for the case of equal mass transfer rates. So when we say that the new volume is 100 times the original, this is what we are talking about, right? V2 is equal to 100 V1. The ratio V2 over V1 obviously is 100, and the ratio R is V2 over V1 raised to 1/3. So we are not able to use the tank diameter relationship because we're already given a relationship that's directly coming from the tank volumes. Let's calculate this. It's 100 raised to 1/3. And that is 4.64. This is our scale ratio that we're going to use. No? For R equals 4.64, how do we then determine the new parameters? It's very simple. You simply multiply the scale ratio R to the existing lengths. So for the first four parameters here, all of these are length units, right? It's just a simple multiplication with R. So that means that my tank diameter from 0.61 meters, I'll multiply that with 4.64. The new tank diameter is 2.83 meters. Impeller diameter from 0.203 meters, that is now 0.94 meters, 0.942 meters, keeping the same number of significant figures. For the baffle width, sorry, not baffle width, for the impeller width of 0.0405 meters, the new blade width is now 0.188 meters. And for the baffle width, originally 0.051, it's now 0.24 meters. That's it. The new dimension is simply R times the original dimension, at least for this 4 right here. No? Everything with the dimension of length, you can make use of that. That the new dimension is simply R times the old or the original dimension. It's a different story for the impeller speed, right? As we've mentioned before, for the impeller speed, we have a different correlation. It's N1 over N2 is equal to R raised to small n. And you have to select here if what case do you want. Our case, of course, is equal rates of mass transfer as stated in the problem. Equal mass transfer rates. Therefore, small n has to be 2/3. I think these are also in the handbook. Let me check. Or it was not mentioned. This is total volumetric flow rate. This is also the, if you notice, this is the same as the flow coefficient, which we have talked about in pumps. Flow coefficient is also applicable for agitators. This is blend time. Okay, it was not provided here. So just remember this, this values for the exponents. This is for equal mass transfer rates. So it's n1 over n2 equals r raised to n. Therefore, we can get n2. N2, you can do this by shift solve, or you can rearrange this one. N1 is 275 RPM. We're looking for N2. That's equal to R, which is 4.64, right? Raised to N, which is 2/3. I'm getting 98.85 RPM, or 98.9 RPM. Okay? Your new agitator has to rotate slowly or slower compared to the original agitator because you increased its impeller diameter. And remember that we are consuming the same power per unit volume. That's why for the bigger system, for the bigger blade, it has to rotate slower. But as you can see, even if it's rotating slower, it's still delivering the same rates of mass transfer, meaning it's still the same efficiency of mixing, just in a bigger volume. Okay. Now, for the power, you can go uh, through the same method that we did for part A, that you have to get the Reynolds number, then get the power number to get the power. But remember that for this case, if you want to get equal mass transfer rates, it means that you also have equal power per unit volume. As mentioned here, equal rates of mass transfer is the same as saying equal power per unit volume. Therefore, even in the original agitator, the power per unit volume is 846.19. This is watts per cubic meter. In your new agitator, it has to stay the same, 846.19, because that is our case for equal mass transfer, right? So in that case, the power per unit volume is 846.19 watts per cubic meter. What's only going to change now is your total volume because your tank is now bigger. The new power would be the power per unit volume, 846.19 watts per cubic meter, multiplied by the new volume. The new volume is pi over 4 times the new tank diameter raised to the third power. The new tank diameter is the one for the bigger one, is this one. It's 2.83 meters. That's what we're going to use to estimate the new power. Cube. Cubic meter will cancel out. You will be left with watts. Power is now calculated as 846.19 times pi over 4 times 2.83 cube. The new power is 15,063 watts. And as you can see, you have a bigger tank overall now. All of your physical parameters got bigger, right? Tank diameter, impeller diameter, blade width, and baffle width all became bigger by a factor of 4.64. Your impeller speed was lowered to only 99 RPM, but your power also got bigger, which makes sense, right? Because you have to now mix a lot more fluids. Your new volume is 100 times the original volume. And that's how we scale up or scale down agitation systems. It's just by using the scale parameter R. Just remember that the scale parameter is just related to the ratio of the volume of the tank volumes raised to 1/3, or you can use tank diameter ratio in order to get the value of R. Once you get the value of R, it's directly applied to all of the parameters of the original agitator. And that's it. You now know a lot of the basic stuff about the design of agitator systems and how to estimate their power requirements and how to scale up or scale down. That's the end of this video lecture. Thank you for watching and good luck.